maybe just some clarifications, okay? I wrote sometimes matrix transposed and then a function applied to it, or a vector. And sometimes I wrote vector transposed and then, I mean, depends if I have the t outside or inside. Is that clear? It makes no difference, right? When we're writing phi, a function applied to a vector or matrix, what we mean is that I take this function and apply it to every entry, right? So it doesn't matter if I first apply the thing to every entry and then rotate it, or if I first rotate it and then apply it to every entry. Clear? So phi of whatever, a matrix transposed is the same as phi of inside matrix transposed. Clear? Okay, these two things commute. Okay, not everything commutes, but this commutes. Okay, good. There were some other questions. I think you will soon get information about your first project. I think it's pretty much done. They're just doing some sanity checking. It was a lot of work, but I think you will get soon some feedback. Yeah, also there was a question, what is exactly the difference between supervised and unsupervised? I'm not sure there's a definition where in every case it's clear, right? I mean, here clearly we get the data by, from the users. In the second one, well, we just have the corpus of text, right? We are not giving anything. And so that's why I think it makes sense to call it unsupervised. But you could also say, well, there's some algorithm that runs it, creates the similarity, and I don't know, maybe you think about that as supervised. I'm not sure there's a definition that, at every single case you will be very clean to understand. But I think typically it's fairly clear, right? I mean, typically you either just get data or you get data plus labels, but I'm sure there are scenarios where perhaps the distinction is not so 100% clear between the two, okay? So now, we talked about one way of this feature selection, and this was matrix factorization. So let's talk about another one that's very often related to, sometimes to graphical data or data that we have. So what is it that typically we have? The matrix xt, right? What is it? Well, these are these feature vectors, right? And what we have is that, right? We have x1, the first sample x2, and we have xn, and right, so we're having n possible samples, and we have a length d. And so typically these are entries, real valued entries. These are just vectors, right? So that's what we get when we do unsupervised learning. Now, sometimes this d might be very large, but we might suspect that most of these features in there are completely irrelevant, right? And so either we might want to get rid of them because perhaps computational problems, or whatever, maybe space problems, or anyway we suspect that it's not useful. So let's assume I wanted to compress somehow this to something much smaller. Okay, so what I wanted to do is maybe this is like whatever 100 of those. Okay, but let's assume I want to represent this all in one dimension. Okay, I want to compress this. All I'm allowing you is to kind of keep one feature. But this feature doesn't have to be one of the existing features. It could be some combination of the features that I have. Is that clear? So I want the data that is maybe 100-dimensional. I want to represent it in one dimension. So that brings us to what's called principal component analysis, or SVD, which we'll talk about in much more detail. But the basic idea is very simple to explain. So I want to project this onto just one dimension, which you can think of, what does this, what it means. So now these data points in high dimension, right? So I've originally these data points in some high dimensional space. And now I want to find some direction and project this data onto this one direction, right? So that all my data now just sits on this one direction. And now my new data points will just be these points that I have here. Is that clear? Okay, so I mean, maybe 100 dimensions, but I want to project it down onto a single dimension, right? So how can I do this? I just pick one vector, right? And the question is, what vector should I choose? And now I just project my thing onto this one vector, right? And that will be my new representation. Now, okay, so now the question is, of course, what should you pick, right? What could be a criterion by which to decide? Now, it's unsupervised. You don't know anything. You don't really know yet what to do with it. So what could be? So we kind of need a meta idea of what would we like to see on this one-dimensional projection? What could be an indication for the fact that I haven't thrown everything away? right? So, just it's kind of clear, right? So let's assume I have this, and it happens that each of these things here was 0, right? Then obviously it wouldn't be a very smart choice to pick that last column or the thing and project everything on that, right? Because they all look the same, they're all 0, right? Not a good choice. So, again, it's not like we're not asking for math right now. We're just asking for maybe an intuition idea. What could be a meaningful criterion? And this last example should be a guiding principle. How much? They're different from each other. Okay, so one thing I could think about is that maybe, so we'll get now points here, right? So we'll get points here on this thing. And I can think of these points as a distribution, right? I can think of points that come from a distribution. And so clearly there will be a mean, right? So there will be, of these points, there will be an empirical mean somewhere. But there will also be, if I'm thinking of the empirical distribution, there will be a variance on top of that, right? And so one thing, and that's exactly what SVD does, is it chooses, once you have to fix the data, it chooses a direction such that the variance of this data that you get, the empirical one, is as large as possible. And the idea is, and again, this might be correct or incorrect in the case you're interested in, right? The idea is that at least, there's still some dynamic range that you have in here to distinguish things. Of course, since you don't know yet what you're going to be interested in, yeah, there might be dynamic range, but about something completely irrelevant, okay? But at least there's something there. Make sense?
Can you please explain once again the variance of what should be like regional maximum?
Okay, so these are vectors, okay? So these are points like here, okay? Now I want to only keep one number per vector, but it doesn't have to be a component that you have, okay? So the idea is I just take a vector and I take a direction and I project it onto that, okay? So I just want a one-dimensional representation. I take this vector, then I can represent it like this. So when I project it on this vector here, okay, then the point will be that now, I get some points that I have here, okay? Now, depending on what I pick, I will get different distributions, okay? So just think about it that I have lots of points. Then I can really think about that I get a probability distribution here, right? So just, let's think I have many, many points. Now, what are the two most important characteristics of a probability distribution? First one is the mean. But the mean we typically know, we just take it out, right? Typically the mean doesn't tell us much. And the second one will be how spread out it is. Once I've removed the mean, it will be the variance of this thing, or the empirical variance. So one idea, okay, could be, how should I, transform the data? Or how should I, what should I pick such that whatever I get out has the highest variance of all possible such representations, okay? And that might be a reasonable thing to pick. Again, it's not clear that that's the best thing because yes, there might be a high variance, but it might be completely irrelevant to maybe something that I later have to do because I haven't specified what it is, but it might be reasonable, okay? And so I can, of course, not just do this to one, but I can also do this if I'm interested, let's say, in 2 dimensions, right? I give you 2 numbers, then I can ask the same thing. So now I have a 2-dimensional distribution. And so there will be a certain component that's called the principal component. Okay, that's the one that has the highest variance, and then I can have one that's orthogonal to it that has the second highest variance, given that I've taken out already a component in the first one. And that's exactly what principal component analysis does. Okay, and SVD is just the algorithm that does it, and we'll learn it. Okay, so it's a meta idea of how to choose these. It's a little, I'll just talk now about 2 examples, and in the notes you have them in there, just explain what it is. It's used very often, but there's a little bit of caveat. And the caveat is that that is not invariant to any scaling that I do in the data. So these principal components or axes, okay, they, if I take the data and I think, for example, I just rescale, for example, certain components, right? Typically we learned that in the beginning what I should do is I should rescale the features, take out the mean, take the variance one, and so on. If I did this in a slightly different way and maybe scale some components differently than other ones, I will get different principal axes or components, okay? And so that should worry us a little bit because the way we normalize the data, there's nothing, it's not like God-given, right? It's not like that has to be like that. We just do it because it's somehow good practice. But if someone did it slightly differently, they would actually get a different result, right? And so there's quite some degree of arbitrariness in there. And so you should just be aware of this. People do it frequently. It's something that's very popular, but it's not completely principled, even though it's called principal component analysis, okay? Because it has a large degree of arbitrariness in there, okay? But nevertheless useful. So the two examples you have in your notes, they're kind of cute, okay? And so one is actually from a PhD student from here, I think was Etta. So what he did is the following. You can, oh, actually maybe this I don't even have. One is I think something about genes, okay? So it goes as follows. So you have the map of Europe. Okay, so here's somewhere CH, and then there's the rest, whatever, okay? And so you have a map of Europe, and so what people have done, you take some genetic markers of people, right, whatever, you go Spain, Romania, whatever, okay? And you take some genetic markers. I don't even know exactly what it is, also not very important, okay? So these are numbers. You create this thing here, right, this matrix here of features. You keep the first two principal components, and now you project this data back onto these two principal components. And of course, these principal components in space might be something like this. Maybe they look like something like this. You just then represent it in the right orientation, okay? And what you get back, voila, is the map of Europe. Is it clear? Okay. Now, the first time you see it, it looks really cute. Of course, you have to be a little bit suspicious because, as I said, there are quite a few parameters you have in there to play with, right? For example, if you take, it makes no difference if you take the axis principle like this or that, orientation. So there are quite a few things that you can do to play with. I don't know how many things they tried before they got the map of Europe, okay? So, it looks, of course, very cute to see that, but, is it completely, did it just jump out like that and, that's it? Or is it, you just play around so that you see it? Okay, right? The other one is, what was the other one? I think it was something about voting patterns. That comes from a student from EPFL here. You look at voting patterns in Switzerland in the various cantons. Again, you look at some two-dimensional representation. Again, you do this matrix. Again, you take the two principal components. You get back the cantons. You just look at the voting pattern of people, and then you get basically the cantons back. You see the Röschtig-Graben, etc. Okay. So again, of course, it's just two-dimensional. You have quite a few degrees of freedom. Question is, how much do you have to play? How many other versions could there have been where you wouldn't have gotten the map of Switzerland, but maybe you got the map of Austria or whatever? Okay. So you have to be a little bit careful. Okay, but it's still quite cute, and it's kind of useful. Good, so this was principal component analysis. We'll spend at least one lecture about this. Next thing is something that we'll probably do still, I don't know if we start today, but it's called clustering. And this is perhaps the most obvious thing, right, to do. If I give you data, let's assume that's the data I give you. I only give you the features, right? So this data is not labeled by whatever, blue and red or 0 and 1 or cats and dogs. I only give you this data, right? Then if you look at it, then it's kind of obvious that there's something interesting happening with the data, right? It's kind of obvious that there are two possible clusters in here. And so, it's intuitive that, or hopeful, that these two clusters will have something to do with what you are interested in. Make sense, right? And so, we'll see some examples of how we can find these clusters. Now, the problem is, of course, typically we don't get data in 2 dimensions. We get data in 100 dimensions, right? And 100,000 points, you cannot see this anymore. So you need a procedure to find these clusters. But it's quite intuitive that you can find these clusters and that you have, of course, again, a lot of degrees of freedom. These are maybe points in real space. So maybe what is a cluster? A cluster is something where the points inside the cluster are closer than the points across clusters, right? So these are 2 clusters, and I think we would all agree that these are 2 reasonable clusters here, right? Why? Because these points here, these distances here, are smaller than typical distances that you have across, right? So it's an intuitive notion here. Now, of course, you couldn't just have two. You could have several clusters, right? Also, you know, so you have what are the choices? What is the similarity metric that you pick between the points? Sometimes it's obvious. If these are points in space, Euclidean distance might be a good choice, but there could be many other distances that play a role. The next question is, how many clusters do you want, right? If you look at that right here, then, you know, for example, if I didn't do this around here, right? So we could, you know, we could now argue whether it's natural that this should be 2 clusters or 3 clusters, right? Again, you know, that's a parameter that you have to put into the algorithm or you optimize something. But it's clearly meaningful to do this. And often you can even do more, right? Often it's even that you could, for example, not just cluster, but you can do even what's called hierarchical cluster. So you first look at maybe saying, so let's assume these are 3 clusters here. Okay, these are 3 principal things. But then perhaps I could look at now this and say, okay, maybe these are also clusters. Okay, these are 2 clusters within the clusters, right? So this is what's called hierarchical clusters. And if in your notes you have an example which has to do with some cancer research, you have different types of cancers where you do this hierarchical clustering, and you can kind of see similarities between them. You know, you see some main groups, and then you see off them again some main groups going off. And so, you know, so clearly you might learn something interesting about looking at the clusters. Maybe you know within one cluster for one particular cancer that a certain kind of treatment is very effective. Then it might be, you know, it might be intuitive that if you look at another cancer in the same class, that perhaps that might also respond well to the same treatment, right? So that nobody hasn't given me any information about these cancers other than have some kind of measurements. And from these measurements and similarities, I can kind of find some interesting structure from this data, and that might inform my decision later on to do something. Okay? So that's what's called clustering. There is another kind of nice thing for clustering that has to do again with text, and that goes towards what's called topic models. So topic models themselves is not really clustering, but you can use it in this context. So what are topic models? Well, we talked already about how we can represent words as vectors, but what is if we want trying to understand whole documents, right? And so sometimes I would like to find, or we would like to, as a starting point, find models that, you know, that represent or model whole text, a whole paragraph, or a whole document, right? And so now, of course, that's quite complicated because language is quite complicated. It doesn't just have words. It's not just a random accumulation of words, but, you know, there's grammar, there's all other kinds of styles, etc., right? So the simplest kind of model that you can think about is where you abstract all kinds of grammar, okay? Wouldn't this be great in high school? No grammar, okay? Don't have to deal with that, okay? So no grammar, okay? But you still want to keep something. So what is it that you want to keep? Well, you can think of that a document is made out of certain topics, okay? That maybe in a document, maybe certain paragraphs talk about certain topics, and as the as the document goes, maybe there's a sequence of certain topics, right? And there might be a certain prior of different topics, whatever. You know, in sports, there might be certain structure of this thing, depending what sports they're talking about, whatever. Now, what is a topic? How do you want to, model a topic? Well, the way it's done in here, in the simplest case, is that it's simply a probability distribution over words. So all you do is take your dictionary, 50,000 words, right? And a topic is simply, and again, all grammar and so on is abstracted. A topic is simply, okay, a certain topic might be, whatever. Tennis has a 0.1% thing to appear in there, and a certain set of words and their probabilities. Is that clear? Okay. So if you look at a paragraph about tennis, and you see 1,000 paragraphs of tennis, and whatever, then you might find that there's always, there's very high likelihood that certain words appear there, right? And if you look at the top 100 words that appear there and their probability, it might make sense to give a distribution, to define a typical distribution what a tennis paragraph might look like, okay? Now, of course, it doesn't mean that the paragraph, and then you just think about that such a paragraph is simply random sampling of such words from that distribution, Okay? Now, of course, you throw a lot of things away. Not every, hopefully a real paragraph is not just like sampling randomly from the set of words, but you kind of different, you can still see that if you talk about politics, or you're talking about the US, or you're talking about whatever, that clearly these distributions would be quite distinct, and that some information would be preserved in there, okay? And so if you have a huge corpus of text, you can define many such probability distributions, which might correspond to topics, but there might be billions of them, and at the end what you have to do is, you can't keep like a billion topics, right? So you just want to maybe just keep the 200 most topics that, most common topics. So how would you do it? Well, I've given, whatever, 1 million probability distributions over this set of words. Okay, each of them is a point in space. All I want is now to define 200 kind of representative topics out of those, right? What is this? This is just clustering, okay? I just want to find cluster of probability distributions that are similar. I'll pick a representative out of this, and that I could call a topic. Okay, again, we're not talking about the details right now, but does the basic idea make sense? Okay, so if you have whatever, politics, whatever, the words might be USA, whatever, okay, too dangerous, okay? But, but whatever it is, I think it should be clear, right, that for every topic you have, there would be, if you look at the top 100 words and you look at their distribution, they could be quite different, right? And all you're asking for is, given a huge corpus of text, give me 200 representative distributions, right? And then each of them, and they should all be quite different, and then there should be a lot of them around, and then each of them I call a topic, right? And then later on I think of documents as just being collection of such topics. Okay, so these were some examples of feature selection. Maybe let's talk also a little bit, and I guess that's all we'll do today. Let's talk a little bit also about the other kind of things. So okay, so let's maybe mention two other things. Again, just mention them quickly. Okay, so these are two other techniques that are often used in an unsupervised fashion. And so let me just mention them. So the first one is what's called autoencoders. And the idea here is this is something that was invented in the realm of what's called neural nets, and we'll talk about it later on. We'll not talk about in detail about autoencoders, but we'll talk about neural nets. And the basic idea is kind of also intuitive. So, so I have a feature vector, let's say x, right? And so this one we can think of both as feature selection, but also as a generative model. So let me first say what it is, and then we can maybe discuss how this fits in. So you have a feature vector, and maybe this feature vector is fairly large. Okay, so this d, the dimension is fairly large. So let's assume now I had the following. I had a function here to something much smaller. So this would be my model here. Okay, so f of x, and this gives me an x prime. And this function is such that this compresses it to something much smaller. Okay, so whatever. The first is maybe 100 dimensions. The second one is 5 dimensions, whatever, right? And now let's assume I have a second, and this is of course parameterized by some w, and I'll learn this, okay? We'll see how this goes. But let's assume I had now a second map, okay? Maybe, I don't know what I call it in the notes, maybe g prime of x prime, and I get here an x tilde, right? And now this x tilde actually lives again in the large space D. And so you should think of the first thing as something that kind of compresses, and the second thing as something that expands thing. And let's assume it happened that for the data that you give me, if I'm looking at the composition, so if I'm looking at x minus g double prime of f prime of fw of x, if I'm looking at this, and maybe I'm looking at the squared norm or any other norm that is interesting, let's assume that this is small for the data that you give me. Okay, so you could learn what's called you could learn the first function and you could learn the second function, such that both together, I can first take my data and kind of compress it into a much smaller dimension, and then I can expand it again to the large dimension. And just for the sake of clarity right now, let's assume I have no error. It's perfect, okay? Of course, in general, we'll have an error in there, right? But it's relatively close. Clear? Could that be of any use? So it could be used, right? And so let's assume small. So such a thing would be called an autoencoder. So where does the autoencoder come in here? So first of all, this is kind of like a compression scheme, right? So you take this input data here, you compress it to something smaller, but then you can expand it again to something that looks close to the original one. Now, why is this, what does the order come in here? The order comes in here is because the way you train it. So typically what you do is that this is represented by a neural net that has parameters here. It doesn't matter what it looks like. It's just a function parameters by W. This is parameters by neural net, and you train it such that end to end, this error is small, but it does it automatically. Okay, so the training itself will give you the function f, presumably, let's assume it exists, and the function g, such that this is more or less true. Is that clear? So you have a vector of d, you decide by the structure how small it should go down, and now you try to learn by training, by fixing the w and by doing an algorithm, it will be against stochastic gradient descent, to find what is the w and the w prime, such that the f composed with the g is more or less an identity function. Okay, and since it does it itself, there's no supervising there. There's no expert there says that's how the data should be compressed. It's all done automatically. Okay, it encodes the data, it compresses the data. That's where the encoder comes from, and the order is because it just does it automatically. Okay, it doesn't. We don't have someone that says, okay, compress it like this. It trains it by first compressing it. It has to compress it because it has to end up with something small, and then it can expand it again, and since we have the end criterion that it has to be close, that's how it finds it automatically. Okay? So on the one hand, we could use that to compress the data, right? So if I have data and I don't want to store that much, then maybe this might be a good way to compress it. On the other hand, this is again like a feature selection, right? Kind of automatically, right? If this was really a very good representation, then rather than starting with the big vector x now for my learning task, perhaps I should just start with the x prime. It's a much smaller vector, and presumably it still preserves most of the information because I could just expand it out to get my original vector. Is that clear? Yes? You guys don't seem convinced. Huh? Can someone ask me a question? Yes? Sorry? No, there will not be linear in general. No. So this will have nothing to do with the schemes we have so far. This will be a neural network which will be nonlinear, but it simply wouldn't work well with a linear scheme, but in principle it has nothing to do with this. Okay? So I start with a large data vector. If I manage to compress it down to something very small, such that from this there's another function to go back to the original vector, and the difference between the two for most data is negligible, right? Then clearly my original vector and this compressed one, they're essentially the same, right? The data might just look to be very high dimensional, but perhaps it's just very high dimensional because it's some kind of what's called a manifold, a much lower dimensional structure in a very high dimensional space, and this algorithm might find it, okay? Maybe all the data is on a sphere, right? Maybe it's a sphere, or some plane in some high dimensions, and I find that that it has a nice structure in there, right? So that's one way to use it. I could use it either as a compression algorithm, right? Or I could now, so far I have only used the data, I've only used the x, okay? There's no feature, nothing what I want to learn is in there. But I might have lots and lots of unlabeled data, right? And I can use that to find a good representation. And now I can start with this small vector and do my actually training for whatever I'm interested in, classification, regression, okay? But starting with something that's small might be better, right? Because it might be easier to learn in a low-dimensional space than in a high-dimensional space. Okay, so here I could use a large amount of unlabeled data just to find this representation. And then I could use some labeled data together with this representation to do whatever learning task I have. That makes some sense? So this would be feature selection. But you can also think about it as kind of a model. Okay, what do I mean as a model? Let's assume that this was really a perfect representation here, and that that's as compressed as possible. Okay? Then it should also be true that on that space, whatever we are operating on, that it should be basically a uniform distribution, and the various components should be independent. Why? If the components weren't independent and it wasn't a uniform distribution, then if any of you that take information theory, you should actually be able to compress it more. Okay? So this means that that representation actually here, this should be a fairly compact representation where the distribution here should actually be very simple. And so if you now forget about this, okay, then you can also think about as a model of how to generate that. Okay? How? Basically pick something more or less uniform on this and just take this function to generate a sample. That should be very close to the actual samples that you get. Okay? In that sense now, it's a generative model. Okay? It allows you to generate samples, or it's at least conceptually an idea to generate samples. Okay? A little bit tricky. What I told you is a little bit tricky. Why? What I tell you, this makes sense if all these things are discrete values. Okay? Often these things are, of course, continuous values. And then what it means to compress is not so clear, right? You all know that you can take two real numbers, right? You can make out of this one real number such that the map is lossless, right? Clear? Right? I mean, there's, you can always map. There's no, I mean, the cardinality of the two things is the same, right? And you can find mappings, of course, not useful mappings, that would not lose any information, but clearly wouldn't be useful. Okay, so compression, when we talk about real valued things, what exactly that means is a little bit tricky, right? But it's intuitive that if I give you vectors in 100 dimensions versus vectors in 2, and the mapping are reasonable in between, that the two-dimensional one is a more compact representation. I don't get a very good vibe here. Any questions? Okay, then let me try to amaze you with the last example, okay? Well, that's really the last thing. Okay, so this is what's called generative adversarial networks. That's something that has become super popular recently. And that's a very nice idea too. It's not something that we will talk about later on, but the idea is very cute. And it's the following. So now what you do is you basically, you have some data, you have some examples. And now what you're trying to do is you're trying to come up with an automatic schemes to generate more examples. So what could be, what is a practical example that you see, and in your notes you see that? Maybe you have like 10,000 pictures of modern living rooms. Okay, these are all pictures. There's a table and a vase and whatever, whatever is in a modern living room. Okay, and so now what you want is you would like to, there might be problems, for example, with copyright about using a picture, or maybe you want to use that for games. And you want that every time you enter a new room, it should look different. So you don't want to just use the pictures you have. What you would like to have is a network that automatically generates for you pictures that a human being cannot distinguish from an actual real picture, but it's an artificial picture that looks like a living room. That's the task. Okay? And there are many other such tasks. So what you want is a generative model for pictures of a living room. Okay? That's clear. So how do you do this? Well, you find some model that gives you something that maybe looks like a living room, but has a lot of parameters that you can tune. Okay, and so you could use like a neural net for it. And let's assume you have, there's some model. Okay, we're talking not about now what this model looks like. That has parameters, and every time you put in some random input, it will give you some picture out. And perhaps it looks like at the beginning, this will just look like some random pixels. Okay, it will not look like anything like a living room. Okay, so let's assume you had a machine like that with lots of parameters to play. Now, what you want is you want to train these parameters such that at the end, this thing actually gives you things that look like pictures of living rooms. Okay, so how do you do this? You do this following. So you have this machine. Okay, so this has a parameter W, and the aim is that this should generate pictures of living rooms. And the way this works is that you just put some random numbers in here, okay, so to generate new samples of this living room, and you get some picture out. In the beginning, this will look horrible, okay? It would look like my drawing, okay, whatever, okay? That's our living room. Now you have also actual pictures of a living room, okay? So you have an actual repository of pictures of a living room, okay? So there is your database. And now what you do is you have another machine, and that's a classifier. So again, you can use whatever, either the classifiers that we have talked about, or again, use a neural net. And what do? Once you have trained you have some particular training of this model, now the classifier also has parameters. So what does the classifier do? You give now the classifier either a real picture of a living room, okay, or you give it samples from this artificial living room. And the task of the classifier is to tell you whether you think it's an artificial picture or a real picture. Okay, it should just be able to distinguish that. So the aim is now the following. These two things are adversaries. Okay, this guy should try to make as good pictures as he can. This guy will try to find, no matter how good this guy is, will try to be able to distinguish the two. Okay? And now what you train is you train them, in rounds. Okay? Given something that generates pictures, you try to find the best classifier until the classifier can actually distinguish. Okay? Then, okay, given, with this, now you fix the classifier and you try to improve the thing that generates the pictures until it can actually fool this classifier. Okay? Then you're trying to, again, fix the one that generates the pictures and try to find a better classifier. And so this is an adversarial, it's like a game, right, where you go back and forth. And amazingly, it works, okay, in some settings, mostly with pictures. And you can see, in the notes, there's some description, and you can really see often pictures. Now, of course, you can imagine that game developers are, crazy about it, because basically you can find now models. Doesn't have to be just living rooms, right? Could be any scenes. You can even think about creating movies or movie scenes, right, where you cannot distinguish anymore between artificial ones, like backgrounds, things that might be very hard to generate if you want to do it explicitly, but that like something like a neural net can do fairly easily, and that can actually even fool human beings. Okay? So there's an generative model, which is this, and then there's this adversary that tries to think, and by the training, that's why it's called generative adversarial models. So next time we start with classification. So what we will do is classification, matrix factorization, word to vector, and then we'll talk about neural nets. Okay?